Hello, hello, hello. There are at least a dozen lectures, 1 hour lectures, by people who argue that the lecture that I gave is all wrong. And though then in their lecture they tell you what was wrong in my lecture and how it should really be. These lectures are most amusing. I have watched several for only 5 or 10 minutes. In all cases, of course, these are people who do not understand physics. They don't have a solid background in physics. So when they approach me, I never argue with them. I teach physics, and I don't argue with people who think they know, but who don't. But if you ever get an opportunity to watch some of those, it's very interesting. Yeah. Okay. There is one issue in physics which is extremely difficult. It is so difficult that many physics students don't get it. What is worse, that there are physics teachers who don't get it. In my 802 lecture number 16, I do a demonstration which blows their mind. It blows their mind because it shows that Kirchhoff's loop rule doesn't apply. The result that you get violates Kirchhoff's loop rule. And that they cannot accept because they have a religious belief, probably going back to their high school days, that Kirchhoff's loop rule always works. So there is one video, 1 hour video, I watched it only very briefly, in which this person says, look, Kirchhoff's loop rule must always work, so the demonstration that Professor Lewin did at the end of the lecture is bogus, it's wrong. Okay. So I decided to once more address this issue. I already did earlier in a video which has a very provocative title. And the title is Kirchhoff's loop rule is for the birds. You can imagine what that did to all those people who have this absolutely 100% belief in Kirchhoff's loop rule. So when they read that lecture, they almost get a heart attack when they watch that lecture. So the title of that lecture is Kirchhoff's loop rule is for the birds. Today I'm going to ask that question again, but not in a provocative way. The title of this lecture will therefore be, is Kirchhoff's loop rule for the birds? And then at the end, we will decide yes or no. You ready? Here we go. I'll take my hat off because it's warm. Okay, I want to make sure that you can see the entire page. Yes, you can. Alright, I have a very simple circuit here. A battery, 1 volt battery, plus side, minus side. 2 resistors in series, 9 ohm here and 1 ohm here. Well, V equals IR. The total resistance is 9 ohm and 1 ohm. The battery has a 1 volt potential difference. So the current is 0.1 ampere. V is 1. R is 9 plus 1, so I is 0.1. If now I do a closed loop integral of E dot dl. Then according to Kirchhoff's loop rule, you should find 0. So you go in this direction. You account for this potential difference. I will do that shortly. For this potential difference and for this potential difference, and when you come to A, the sum of those potential differences will be 0. But if you had gone this way, you would also have found 0. So let's do that together. We go in this direction and let's start at A. The current is in this direction, so the E field is down here and the E field is up here. And inside the battery, the E field is from the plus to the minus is in this direction. Those E fields are not at all necessarily the same. But certainly E is down here, it's up here, and it is in this direction here. So let's start in A, and let's do the closed loop integral of E dot dl. That means adding up all those differential potential differences. From A to B, the integral E dot dl, the potential difference from A to B, is plus 0.9 volts. I is 0.1 ampere, the resistance is 9, so that is plus 0.9 volts. Electric field is in this direction, so when I go from B to C, again I get I times R. This is a higher potential than this, so I get plus 0.1. Then I go from C to A. This side of the battery is plus, this side is minus, so I go against the electric field. And that means the potential difference between C and A over this route is minus 1. Because A is plus 1 divided by C. So 0.9, 0.1 minus 1 is 0. Yeah, that's what Kirchhoff predicted. Beautiful. Let us only go from A to B and calculate what the potential difference is when we go from A to B. And let us first go from here to here. And then we stop. Well, the current is 0.1. The resistor is 9, so VA minus VB is plus 0.9 volts. High school physics. Let's now go from A to B this way. I go from A to C. I go in the direction of the E field. So A has a higher potential than C. And the difference between A and C is plus 1 volts. You see it here. From A to C gives you plus 1. Then I go from C to B. E field is in this direction. So B has a higher potential than C. So VC minus VB is minus 0.1. There is your minus 0.1. And 1 minus 0.1 is plus 0.9. Isn't that wonderful? So the potential difference between A and B, whether I go this way or whether I go this way, is the same. It's path independent. That is intrinsic in Kirchhoff's loop rule. Whenever you have a circuit whereby the closed loop integral of all the potentials, the integrals of E dot dl, closed loop, if they are 0, then the consequence of that is that if you take 2 points, no matter where you take them, and you measure the potential difference between those 2 points, no matter which routing you take, you get the same answer. Let us go from C to A. From C to A. And let's first go this way. Well, A has 1 volt higher potential than C, so VC minus VA is obviously minus 1 volt. Integral E dot dl from C to A minus 1 volt. Now I go from C to A this way. I go against the E field, so C has a lower potential than B, and that is minus 0.1. because this is 1 ohm, and the current is 1/10 of an ampere. So VC minus VB is minus 0.1. So now I go from B to A. So I go against the E field. The current is 0.1 amperes, resistor is 9. So clearly A has a higher potential than B. So B has a lower potential than A. So now I have minus 0.1. Now, minus 0.9. Here it is. So now I went from C to B and from B back to A. Minus 0.1, minus 0.9. Hey! VC minus VA, this root is minus 1 volt. VC minus VA in this root is also minus 1 volt. Are you happy? I repeat what I said earlier. Kirchhoff loop rule says that the closed loop integral of this circuit of E dot dl, which means adding up all the potential differences, must be always 0. And the consequence of that is that if you take two random points in your circuit, then the potential difference between those two, whether you go in one direction from point A to B or in another direction, makes no difference. You always find the same value. Are you happy now? Okay. Now hold on to your chair. I have to move my camera. I want to make sure that you can see it. No, not yet. Okay, now you can see everything, I hope. Yeah. I have here a circuit which, again, has a 9 ohm resistor here and a 1 ohm resistor there. And the wires, just like they were in the other case, have no resistance. Let's call them superconducting wires. Keep that in mind, that was also the case in my previous drawing. These wires here have 0 resistance. I have an electromagnet which you cannot see, but it is perpendicular to the paper, and I can turn that electromagnet on. It's an external current, of course. So the B field, in this case, let's assume that it comes out of the blackboard, and the B field rises very steeply, and then after a while it's constant, it no longer changes. During the time that this B field is changing, that it is growing in this case, Lenz's law will say that the circuit will get an induced EMF, that means an induced current, which will oppose the change of this B field. So if the B field wants to increase in this direction, the induced EMF, Lenz's law, must drive a current in this direction, in clockwise direction, because that will oppose the increasing B field in this direction, because a clockwise current will produce a B field inside, into the blackboard. Yeah. You remember that from Lenz's laws, even from your high school days. I'd like to think of it as being Faraday's law, but let's just stick to Lenz's law. Now, at one particular moment in time, the change in this B field is such that the EMF that is generated, the induced EMF in this circuit, is 1 volt in this direction, so that the current will flow like this. A microsecond earlier or later, it was probably not 1 volt, because then the change in the B field was different. But at this moment that I choose now, it so happens that, according to Lenz's law, In my book I call it Faraday's law. The EMF is 1 volt. And that's the moment that I want to discuss with you. So there is an EMF in this direction. Keep in mind that these wires have no resistance. So there is no electric field in these wires. That wouldn't be possible because that would cause an infinitely high current. So the E field produced by this EMF can only be in this direction here and in this direction here. So the E field, the induced EMF, is confined to this resistor and to that resistor. What is the current? Well, the EMF is 1 volt, V equals IR, so I is 0.1 ampere. So there's an 0.1 ampere going around like this. Let's now calculate the closed loop integral of E dot dl. Let's go in this direction. I start here. E field is in this direction. Current is 0.1 ampere. So this point has a potential higher than this point of plus 0.9. Now I go from B to A in this direction. I go in the direction of the E field. The current is 0.1, the resistor is 1. So B has a higher potential than A, which is 0.1 volts. So the closed loop integral now, in going this direction around, is 1 volt. It's not 0. It is not 0. So in this case, Kirchhoff loop rule does not apply. It's as simple as that. Now, I will show you something which of course blows so many people's mind. And I do a demonstration in lecture 16 of 802. You can see it in front of your eyes. This bizarre prediction I demonstrate in a perfect way. Follow me now. Let's go from A to B and we go this way. VA minus VB is obviously plus 0.9 volts. Current is in this direction, 0.1 amperes, 9 ohm resistant, so VA minus VB is plus 0.9 volts. Now I can go from A to B, not in this direction, but I can go in this direction. If Kirchhoff loop rule was holding, I must find again plus 0.9. But that's not what I find. So now I go from A to B this way. The E field is against me. So that means that VA minus VB is negative. The E field is opposing me. The current is 0.1 amperes, the resistance is 1 ohm, so it is minus 0.1 volts. So, in going from A to B this direction, you find plus 0.9 volts. In going from A to B in this direction, you find minus 0.1 volts. That means the potential difference that you measure, if you call that potential difference, is path dependent. I repeat myself, there is no E field anywhere in these wires because these wires have zero resistance. So now, what does it mean now when I say Kirchhoff's loop rule is for the birds? That was a provocative statement. What do we have to conclude? We have to conclude that Kirchhoff's loop rule only works in special cases. And the special cases are all cases whereby there is no changing magnetic fields in the circuit. But in all cases where there is a change in magnetic field, Kirchhoff's loop rule does not work. The closed loop integral is not zero, and the potential difference between 2 points that you randomly pick in the circuit depends on the path. If you now ask me, well, is the potential difference between A and B, is it now plus 0.9 or is it minus 0.1 volts? That's an illegal question. It's both, it depends on your path. Faraday's law, and you will learn about Faraday's law when you take my 802 lectures, will allow you to calculate the induced EMF. I didn't do that here, I simply told you in this case it was 1 volt. But if you watch my lecture number 16, you will see, you will get more information that may help you to understand the demo that I do. In the demo that I do, I show you that 1 voltmeter is measuring this potential difference between A and B, and the other voltmeter is measuring this potential difference between A and B. But 1 voltmeter is placed here, and the other voltmeter is placed there. And that simple fact means that the potential difference is measured over a different path. And I demonstrated at the end of lecture 16, and the result is mind-boggling. You will see that 1 voltmeter shows a positive value, which is much larger than the other voltmeter, but the other voltmeter even shows a negative value. So the magnitudes are not the same, potential difference between 2 points. The magnitudes are not even the same, but they are even reverse polarity. Now, is Kirchhoff loop rule really for the birds? Well, it depends on your definition. When you get to know Faraday's law, you will see that Faraday's law always works. Always. And in the case that there is no changing magnetic field, Faraday's law will tell you that the closed loop integral is zero. Now, you may want to call that Kirchhoff loop rule, I have no problem with that. But if you only, exclusively, your whole life, only use Faraday's law, you're always right. If there are dB/dTs, Faraday's law says, there is an induced EMF. If there is no dB/dt, Faraday's law says, that's okay, the closed loop integral is zero. So I leave it up to you to decide whether Kirchhoff loop rule is for the birds. Let's be nice to Kirchhoff and say, no, it's not for the birds, but you don't need it. All you need is Faraday's law. There are people, including physics teachers, who truly believe that the potential difference between 2 points is not path dependent. Yeah, it's true, they really exist. They say it's impossible. Whether you go left or right, you must find that the potential difference between point A and point B is the same no matter how you go. That is not true. Thank goodness that is not true. Thank goodness Faraday's law works. Because our entire economy only runs because of Faraday's law. All electric power stations can only produce electricity because they have loops and they have changing magnetic fields in those loops. And that generates currents in those loops. And that's the electricity that runs our entire economy. So if Faraday's law, if Kirchhoff's loop rule always worked, electricity could not even be produced in a power station. So, give this some thought. Maybe it will give you some sleepless nights, that's very healthy. If you watch the video by the person who proves, yeah, believe me, he proves that that the potential difference is the same no matter how you go. It's funny, it's amusing. Be my guest. Watch lecture 16 when you're up to it in 802. You may also want to watch my lecture Kirchhoff loop rule is for the birds. But at least walk away after this lecture that you have no doubts about the fact that the potential difference between 2 points in a circuit can be very different depending upon the path. They can even have a different polarity. In one route, A may be higher potential than B, and in the other route, A may be a lower potential than B. Okay? Maybe you don't want to be friends with me anymore. Have a nice day and take care.